problem 1.
Hello everyone, I hope you're doing well. In this video, we are going to solve problem 1 from chapter 2 of solid state physics by Kittel. Let's see the problem statement and we'll dive directly into the solution. So the statement says that consider a plane HKL, these are the Miller indices of the plane, in a crystal lattice. In part A, they are saying prove that the reciprocal lattice vector which have this form G equals hb1 vector plus kb2 vector plus lb3 vector, where hkl are also the similar numbers as these planar Miller indices are, we can notice it, is perpendicular to this plane. So we need to prove that the reciprocal lattice vector G is perpendicular to this plane. Okay, so we need to prove that thing in first part. In second part, we can see that prove that the distance between the two adjacent parallel planes of the lattice is this. Okay, so we'll be considering the same plane and we need to prove that the interplanar spacing is actually equals to 2 pi by magnitude of G vector. It's magnitude of G vector. All right, so that is the second part in which we need to prove that the interplanar space is actually equals to this thing. And in part C, we need to show that for simple cubic lattice, the square of the magnitude of interplanar spacing, all right, is equals to this thing. So these are actually three different proofs that we need to do in a single problem. And first of all, we'll do it for the part A, in which we need to prove that the reciprocal lattice is perpendicular to the plane. Let's do this right away. Let's get started. Consider a crystal lattice. So first of all, what I'm going to do is to draw the plane inside the crystal lattice that we have, the general crystal lattice, and that figure will help us to do the whole proof. Okay, so that figure is the most important figure for this proof, so carefully learn how to do that. Okay, so consider a crystal lattice with lattice parameters. We will be considering the general lattice parameters, which are A, B and C. Okay, C only, in A, B and C directions. It's just like we used to say that it's A, B and C in X, Y and Z direction. Here I'm considering A, B and C directions, which shows the permittive directions of a crystal lattice. Here A, B and C are actually the permittive vectors of the direct lattice, and yes, we are considering them instead of the X, Y and Z directions because we need to compare the direct lattice with the reciprocal lattice, and that is why we are doing it. That here A, B and C are the permittive vectors of the direct lattice. Direct crystal lattice, it's also fine to say that. Till this point we have defined a crystal lattice, how it looks like. It's really simple. Okay, let me draw it in here, then we'll write about our plane. Let's draw this lattice in here. So there will be a common point like that, and let's say there is one direction like that. This is another direction. Let's say it's A direction, let's say it's B direction, and let's say this is the C direction. We don't need to mention any angle between them, that's not necessary. We just need to draw this axis lines and it represents the permittive vectors of the direct crystal lattice. If you join them together in 3D and extend them, you can form a crystal lattice out of it, but we don't need to do that in here. It's not necessary. We are just drawing a plane inside that crystal lattice that has some general representation. Don't be confused. It's just like it's x-axis, y-axis and z-axis, but in general context. All right, so because it could be different, and if you know about the permittive vectors, they are not necessarily parallel to x, y and z axis. They have a combination of them, so we are considering A, B and C. All right, so till this point we have drawn a crystal lattice. Now let's draw the plane inside this lattice. Let a plane with Miller indices H, K, L inside this lattice. If you know, then you know how we draw the plane inside the lattice. It's like we take the reciprocals of these indices. Okay, we'll take reciprocal of each of these indices. Here reciprocal of h is 1 over h, reciprocal of k is 1 over k, and reciprocal of L is 1 over L. Alright, the next step is to multiply the lattice parameters with each of these indices in order to incorporate the type of crystal lattice we are considering. Normally this step is not needed, but when you are considering the general treatment of Miller indices, planes, and all of these things, you need to multiply the lattice parameter with them. So here the first index relates to A direction, the second index relates to B direction, and the third index relates to the C direction. So you will multiply A with 1 over H, B with 1 over K, C with 1 over L. Alright, and these are the final intercepts of HKL plane inside this crystal lattice. Okay, and these intercepts would be used. Intercepts are actually used to draw the plane, and these are the point on the axis line. So this is A intercept, this is B intercept, and this is the C intercept. Just like we used to call them X intercept, Y intercept, and Z intercept. Since we have these axis lines, so we'll call everything in reference to these axis lines. So A by H is A intercept. So let's say it's here. You don't need to be specific, it could be anywhere. Let's say B intercept is here, which is B by K, and let's say C intercept is here, which is, let's say, C by L. Alright, let's join these 3 points together to form a plane. Okay, you can see here that here is the plane, and these are the intercepts of the plane. Alright, and next what I'm gonna do is to draw vectors in here, and let's say this is a vector from this point to this point. This forms a vector, and I'm going to call this point as capital A, this point, and this point as capital B, and this point as capital C. Okay, just to show that these are points. You can use any other wording like P, Q, R, or whatever. So this is AB vector, this is BC vector, and this is CA vector. This is what I'm going to do because I want to prove that G vector is perpendicular to this plane, and for that purpose I need to find a vector that represents this plane. Okay, and by finding out the dot product of G vector with the vectors of this plane, that the vectors that define this plane, I can prove that G vector is perpendicular to this plane. Here what I want to do is to find out a vector that represents this plane. Okay, and we know that the scalar product of two vectors is 0 if they are perpendicular. So if I could somehow find out a vector that represents this plane, then I can find out its dot product with G and prove that they are both perpendicular to each other. Alright, so that is how I'm planning to do, and that is how we always do most of the times when we need to prove the orthogonality or the perpendicular nature of two vectors, lines, directions, or whatever. Okay, so you must be wondering that how we can find out the vectors that represents the plane. Let me tell you that there are always these boundary lines making up the plane. Alright, they could be 5 boundary lines, they could be 4, 5, 6, 7, and least boundary lines are 3. Okay, and we have these general cases. So we can see there are 3 different boundary lines, and these boundary lines corresponds to 3 different vectors that shows the possible directions this plane has. Okay, so we can see this is a vector AB, this is one of the vector of the plane. BC is another vector of the plane, and CA is another vector of the plane. Order doesn't matter, you can call it as BA, AC, or CB, whatever. Order doesn't matter, but it's like these lines. These 3 different lines represents the plane. If G is perpendicular to AB vector, BC vector, and CA vector, alright, if G vector is perpendicular to these 3 vectors, then G is also perpendicular to plane that is formed by these 3 lines, which is actually HKL plane. Alright, this is how we can prove that G vector is perpendicular to the plane. And yeah, let's find out the vectors first, which is AB vector, BC vector, and CA vector, and then we can find out the scalar product with G vector, which is already known, in the question statement. So let's do that. For that purpose, we need to find out AB vector, then BC vector, and then CA vector. Okay, AB vector is actually equals to the final point minus initial point, which is B point minus A point. We'll find these points from the figure. C point minus B point, final minus initial. Okay, here final minus initial, so it's A minus C. Let's see what A, B and C points are so that we can find out these vectors. Here we can see that this is the point A and this is origin. Starting from origin, we can find out its coordinates. Starting from origin, we have to move A by h units to reach to this point, which is actually the intercept. It's really simple. So it's A by h, and it's only in magnitude form. So in vector form, it will be A vector divided by h, since it's A direction. So A vector divided by h will be taken as the A vector, capital A vector. All right, since we are taking the vector form, and here the B point is actually B vector divided by k, and C point, C vector, is actually C vector divided by L. And we took these vectors because they are also the axis directions. That is why we took all of these notations. Keep that in mind. So now we take B vector. This capital B vector was small b vector divided by k. So let's put these values right away. B vector divided by k, which is Miller indices, minus A vector, which was A by h. C is C vector divided by L, minus B is B vector divided by k. A is A vector divided by h, minus C vector, which is C vector divided by L. Alright, simple is that. I hope you are not confused. Now we had G vector, which was hb1 vector, kb2 vector plus lb3 vector. Now it's time to find out the dot products, and let's write it down here that if G is perpendicular to plane HKL, then dot product of G with AB vector should be equals to dot product of G vector with BC should be equals to dot product of G vector with CA, and they all should be equals to 0. Okay, that is the condition. That is something that we are gonna do, and it will complete the proof at the end. So let's calculate G dot AB first. G dot AB, that is equals to G is hb1 vector plus kb2 vector plus lb3 vector, and dot product with AB, which is this. Let's write them in order first. We'll write A first, then B, and then C. Okay, so A is first, minus A vector divided by H, plus, since it has plus sign, B vector divided by K. And we can see that the C vector is 0, so we can write nothing. Okay, then it doesn't have A, so next is B. We are just writing them in order because it will help in finding out the dot product. Then we have C by L. Here A is first and C, yeah, it's already in order, so let's write this one here. Minus A by H plus B vector by K. Alright, let's find out the dot product. And in dot product, the first component B1 will multiply with A only, B2 will multiply with B only, and B3 will multiply with C vector only. It's just like the scalar product works on parallel vectors only, and that is why it's happening. So H will multiply with this one only, so it's H B1 vector dot minus A vector by H. Okay, that is how you are supposed to write. Then plus sign KB with B, KB2 vector dot B vector by K, and since C is 0, this component automatically becomes 0. Alright, you can even do it by writing 0 c vector in here, so it's multiplied and it's 0 ultimately, so you don't need to write it. Alright, let's simplify here. H and H cancels out and it's negative here. b1 vector dot a vector plus k and k cancels out since they are similar. b2 dot b vector. Now what these products are equals to, let me mention here that we know that the dot products between reciprocal vectors b1, b2 and b3 and direct lattice vectors a, b and c, or I'm just writing down the whole relation. It's like b1 dot a equals to b2 dot b vector equals to b3 dot c vector. They're all equals to 2 pi. Alright, and if g vector is not normalized, in that case it is equals to 1, but mostly they take 2 pi. So for non-normalized g vector it's 2 pi. Alright, and it always holds, so you can put the value, putting values, and we have g dot ab, that is equals to minus b1 dot a is minus 2 pi plus b2 dot b, that is 2 pi. Minus 2 pi plus 2 pi, that is equals to 0. So we can see here that g dot ab equals to 0. As we can see that we got 0 for the first product, and let's do it for the other two and see what happens. Here we have g dot bc. We know that g vector is h b1 vector plus k b2 vector plus l b3 vector and dot product with bc vector, and we know that bc vector is actually minus b by k plus c by l, minus b by k vector plus c by l. Let's find out the dot product, and as I told you people earlier, b1 will multiply with a vector, b2 with b, b3 with c. So order matters. Since we don't have any a in here, so this goes to 0. And we have kb2 multiplied by minus b by k through dot product. So kb2 vector dot minus b vector by k. Then plus sign lb3 dot c by l. Alright, so here k and k cancels out since they are scalars, and b2 dot b and this negative sign here plus l cancels out, b3 dot c, which is b3 dot c, and we'll recall this result, we'll recall to this relation. We can call it as equation number 1 or relation number 1, and we can see that we have in here b2 dot b and b3 dot c. Okay, b2 dot b and b3 dot c, they both are 2 pi. So minus 2 pi and plus 2 pi, minus 2 pi plus 2 pi gives 0, and hence we can see that g dot bc is also equals to 0. Let's calculate the last one, which is g dot ca. Alright, and g is again hb1 vector plus kb2 vector plus l some b3 vector dot ca vector. What is ca vector? It's a by h minus c by l. A by h minus c by l and a vectors on them. Let's find out the dot products. So b1 with a, b2 with b, since b is not here so it goes to 0, b3 with c only. So hb1 dot a by h, then we have plus minus minus, so lb3, then c by l. I have already wrote this negative sign here. So h cancels, it's b1 dot a minus ll cancels, so it's b3 dot c. Both of them are 2 pi, and we can see that it is equals to 0, and g dot ca equals 0 as well. We can conclude here, since g dot ab equals g dot bc equals g dot ca equals 0, hence G, which is the reciprocal vector, is perpendicular to the plane HKL. Alright, in that way we have proved it. As we are done with part A, now let's move to the part B, in which we need to prove that the interplanar spaces, or the in which we need to prove that the interplanar spacing between two parallel planes is this. Okay, while the plane that we are considering is HKL again, so let's see how we can do that. And for that purpose, we refer to the similar lattice that we did before in part A. Okay, we'll be writing down the same things in here, but the diagram will differ slightly, all right, because I need to elaborate the interplanar spacing. So but this thing will remain the same because we are considering the same lattice. So consider a crystal lattice with lattice parameters A, B and C, and these are the lattice parameters in which directions? In A vector, B vector and C vector directions, or you can say the axis directions. Is similar to saying that A, B, C or the lattice parameters in X, Y and Z direction, since we are considering the permittive vectors that are really important when we are considering the reciprocal lattice and the direct lattice comparison. So you need to consider A, B, C instead of X, Y and Z here. And yeah, these are the ones. And here we need to mention that A, B and C are the permittive vectors for the direct lattice. Let a plane HKL with these Miller indices inside this lattice, and we have already discussed their intercepts. So their intercepts will be C by L, A by H and B by K. So let's mention them here. We have a single plane. It have intercepts of A by H, B by K and C by L with A, B and C axis. You can mention vector on them or A, B, C. It's totally up to you. It's fine. And that is the lattice that we are considering and the plane we are considering and the intercepts. It's just like we have rewritten the same thing that we did before. Let's draw it. Let's draw the figure for which we were talking about. So for that purpose, I'll draw a parallelogram on 4 lines, 1, 2, 3 and 4 lines. Let's draw them first and we'll see that what this figure is, because it's another parallelogram slightly above the previous one, and we are drawing here a closed figure. Let's join these points together to form a closed figure. All right, let's say this is the A axis. Let's say this is the B axis, and let this be the C axis. All right, and as you can see, this is not the crystal lattice. This is not the original crystal lattice, but we are just taking a chunk out of the crystal lattice. Okay, this is not representing the original shape of the crystal lattice. We have just mentioned the lattice directions that the crystal lattice had, and here we are just highlighting two of the lattice planes, which is, let's say one of the plane is here, because we are interested in interplanar spacing, so we should have two parallel planes inside this figure. So this is one of the plane, all right, and this is another plane, and we can see that both of them are parallel to each other. I'll call it as plane number 2, and let's say this is the plane number 1. All right, and we know that what does the interplanar spacing mean? Interplanar spacing means the perpendicular distance between two planes. So vertical distance between two planes will be the interplanar spacing DHKL. Alright, and we also know that the point where the plane touches the c-axis is the c-intercept, which is actually c by l. We can write it in vector form as well. So this point is c by l. Alright, and this is the origin, you can see, because this is the point where the a-axis, b-axis and c-axis join together. So this point of intersection is actually origin. So now let's see how we can find out the interplanar spacing out of this figure. And you can see, as I told you earlier, again I'm telling you that this doesn't represent the original shape of the crystal lattice. It's just that we have took one of the chunk where the two planes were lying so that we can find out the interplanar spacing and prove the formula that we wanted to prove. Okay, so here you can see that if we draw a vector from this point to this point, okay, this is the point. In other words, you can say this is plane 1 and it is touching the c-axis at this point. All right, and you can see that plane 2 is touching the c-axis at this point. So the perpendicular distance between this point and a corresponding point on plane 1 would be the interplanar spacing. All right, so we just took one reference point, which we took as the c-intercept of plane 2, the point where it touches the c-axis, and also the point where the plane 1 touches the c-axis, which is this point. Okay, so the perpendicular distance between these 2 points will give us the interplanar spacing. And how we can do that? So for that purpose, what I'm going to do is, you can say this is d vector vertically upward. We can draw a reference line in here, and if we have this angle theta of this line of this vector, which is c by l vector, this is c by l vector, you can see that it points from origin to this point, so it makes an angle theta. So the projection of c by l on this reference line gives us two components. You can see here it will give us two components. One is the horizontal component and the other will be the vertical component. This horizontal component is the perpendicular distance between this point and this point. This is actually the perpendicular distance, which is the interplanar spacing. Hence we can see that the d is actually the horizontal component of c by l vector. Alright, so this is how actually we define the interplanar spacing. If you want to find out interplanar spacing, find out the perpendicular distance between, for example, our corresponding point here on plane 2 and its corresponding point in plane 1. You can see this is the point where the plane touches the b-axis, for example, and its corresponding point is here as well. So if you find out the perpendicular distance between this point and this point, it will also give you the interplanar spacing. So we just want to make it as simple and as easy to proceed as possible. So what we did is that we took this side, we make this vector from origin to this point is c by l vector, as we have seen previously as well. If you find out the vector, its coordinates are actually c by l, so its vector is c by l as well. So that is this vector. And if you want to find out the perpendicular distance, not the original, not this distance, we are wishing to find out the perpendicular distance between these 2 points. So that is why we took only this component that is vertically upward, and this component that is vertically upward is actually the horizontal component of c by l. So if you want to write out d, then it would be equals to d equals horizontal component of c by l, c by l times cos theta, that is horizontal component. If you want to find out the vertical component of c by l, it will be equals to, vertical component will be equals to c by l sine theta, but we are interested in cos theta because that is what will interplanar spacing is. Alright, I hope you are not confused in this point, and yeah, that is it. Let's proceed. Here cos theta is something that we don't know, and that is something we need to calculate, and cos theta actually specifies the direction of d. So we can do it using the g vector. We know that the g vector is given by g vector equals hb1 vector l b3 vector. Alright, and let me tell you that g vector and the interplanar spacing vector, which is d, they both are in similar direction. We know that g is perpendicular to plane HKL, and d vector, you can see D is also a perpendicular distance between two planes, hence D is also perpendicular to plane. Since D and G both are perpendicular to planes HKL, it means that G and D are parallel to each other. Hence, D will point in the similar direction as G does, and the unit vector of G is also the unit vector of D vector. Okay, so here that is what we are gonna do. We are gonna find out the unit vector of G vector, which is equals to this vector divided by its magnitude. We'll keep the magnitude as it is because that is something we need in the final formula as well. Let's put the value of G vector, which is hb1 vector plus kb2 vector plus lb3 vector divided by G magnitude. Alright, this is the G unit vector, and this unit vector points in the similar direction as the D vector does. Okay, so that is also giving us the D direction. All right, and we can write it here that since D and G unit vector points in the similar direction, in bracket you can write that the D vector is parallel to G vector, hence we can write the situation that the D hat vector is equals to this thing. So here we have stated that D and G unit vector are in the similar direction. It means the unit vectors are equal to each other, and keep that in mind that the unit vector only represents direction. It doesn't have anything to say about the magnitude of the vector. Hence we can put the unit vector of D and the unit vector of G, since they are representing the similar direction, to be equal to each other. Alright, but we cannot put their magnitude to be equal to each other because it's not necessarily be equal. So hence we'll be putting the unit vector of D to be equals to the unit vector of G. So I'll be writing D unit vector to be equals to this thing in next step, considering that the both unit vectors are pointing and representing the similar direction. So we can write this thing. Alright, and now we can separate this denominator with each of these three quantities because it's denominator common to all these three quantities. It will help us later in calculation. So it's h by G magnitude b1 vector plus k by G b2 vector plus L by G b3 vector. Alright, this is the unit vector of interplanar spacing. Now what we are going to do is we have that we said that D is actually the horizontal component of C by L vector. There is another way to state it. It's like D is equals to the component of C by L in the direction of, but this direction is G hat or D hat. Okay, so we can say that D is actually equals to the component of C by L in the direction of D hat, and we can write it in mathematical form that D is equals to the component of C by L in the direction or we can say in parallel to in the direction of D unit vector or G unit vector. Alright, so we can write D to be equals to C by L dot G unit vector, or you can write it as C by L dot D unit vector. Alright, this is another way to say it, like the component of C by L in the direction of D hat. If you want to find out the component of a vector in a particular direction, just find out the dot product of that vector with that direction and you will get the component. Okay, and this is how we are gonna do it here as well, because we know what is D hat in here, we know C by L as well, so there is no problem at all putting values, and it will help us to complete the proof. So D hat is actually H by G magnitude b1 vector plus k by G b2 vector plus L by G b3 vector, and this is a bracket. Now let's find out the dot product between these. And as I told you people earlier, that A is parallel to B1, B is parallel to B2, and C is parallel to B3. Only parallel vectors are multiplied with each other in scalar product because they are the only ones which have non-zero scalar product. So we'll be multiplying C with B3 only, since we don't have A and B for these two, so they will go to 0 automatically. And we have a product between C and B3 only. So let's do that. It will be C by L dot product with L by G B3 vector. L cancels out, and D equals C dot B3 divided by G vector. And as I told you people earlier, since B3 dot C, that is equals to C dot B3, since the scalar product is commutative, so they both are equal to each other, it is actually equals to 2 pi. All right, so let us put in here, and we get D. This is the magnitude of interplanar spacing, and the direction is already, you can see in this form. We can find out a particular value for it by putting the value of G magnitude in here and B1, B2 and B3. So we'll get a particular value, but that is not a point of this video. D equals C dot B3 is 2 pi. So 2 pi by magnitude of G, which will be written the same way. You can write HKL in subscript because the plane that we considered was HKL in general, and hence we can see, hence proved. All right, that is what we wanted to prove in first place, and we have proved it. All right, so if you summarize everything that we have done so far, it's like we have drawn two parallel planes. Okay, we defined what interplanar spacing is. Interplanar spacing is the perpendicular distance between two planes, and for that purpose we draw this figure of two planes. We consider two similar points on the c-axis. What these points are: the point where the plane is touching the c-axis. Okay, it is this for plane 2 and it is this point for plane 1. We found the perpendicular distance between these two points, and we found that it is actually equals to the component of C by L in the direction of G hat or D hat. Okay, we calculated G hat and hence D hat knowing the reciprocal vector, and then we calculated the interplanar spacing formula. This was all really simple and straightforward. Now let's do the third part, which is linked to the results that we got for the second part. Okay, we have to prove that for a simple cubic lattice, we have a particular lattice now which is simple cubic, simple, not face centered, not body centered, it's simple cubic lattice, that D square, which is the square of the magnitude of interplanar spacing, is equals to A square divided by H square plus K square plus L square. Alright, so using this result, we'll prove this for simple cubic lattice. Let's see how we can do that, and it's really simple as well. Let's do that. First of all, we'll write that we know that what does D equals to? D equals to 2 pi by magnitude of G vector. This is the formula that we'll be using, and you can see that what we need here in order to calculate D, which is actually the magnitude of G vector, and it's not as simple and straightforward as you might be thinking. So let's quickly get started. We have the reciprocal vector to be equals to G vector equals to H B1 vector plus K B2 vector plus L B3 vector. Okay, and you must know that what is the formula to find out the magnitude of a vector given its, the vector form is given. So you might be thinking of this formula, which is square of its x component, square of its y component, and square of its z component. Okay, this is how you can calculate the magnitude of a vector, but the vectors that you are, or the coordinate system that you are using, should be in XYZ coordinate system, not B1, B2 and B3, nor A1, A2 and A3 coordinate system as well, like ABC coordinate system as well that we are using. So the vectors that you are given with shouldn't be in any other coordinate system but this coordinate system, okay, which is X, Y and Z, and hence what we have to do is to convert these vectors B1, B2 and B3 into XYZ coordinate system. That is what we need to do, and after that we can use this formula to calculate the magnitude of g vector. All right, this formula only holds for the xyz coordinate system. It doesn't hold for these coordinate systems. All right, and in xyz coordinate system, these three axis lines are perpendicular to each other, but they are not in these ones. That is why we can't use this formula for these, original vectors. So first what we have to do is to convert b1, b2 and b3 into xyz coordinate system. And we know that for a simple cubic lattice, simple cubic lattice, b1 vector is equals to 2 pi by a x hat, okay, and b2 equals to 2 pi by a y hat, and b3 equals to 2 pi by a z hat. Okay, these are I hat, j hat and k hat, but we are using xyz because we used the similar alphabet notation to represent vector in here as well. So you can use I hat, j hat or k hat, or you can use x hat, y hat and z hat. They are all equal. All right, so these are the reciprocal vectors of a simple cubic unit cell. So we'll be putting these values right back into this equation. In order to get the g vector in terms of x, y and z coordinate system, putting into 3, let's call it as equation number 3. So putting it gives us g vector equals h. What is v1? It is 2 pi by a x hat. Then k, what is b2? 2 pi by a y hat plus what is, it's L into b3, 2 pi by a z hat. All right, now let's write it the correct way, like writing 2 pi first, then h by a x hat plus 2 pi k by a y hat plus 2 pi L by a z hat. This is the g vector in xyz coordinate system for a simple cubic lattice. For other lattice like face centered and body centered, the relations are different. Okay, so depending upon the type of lattice that is given to you, you have to put the values of b1, b2 and b3. Okay, for a particular lattice, it's a particular result. For b1 and b2 and b3, it varies from lattice to lattice. So it's simple. If it's simple cubic, then these are the results that you will be using for the reciprocal permittive vectors, and that is what we used in here as well. Now we can use the formula, which is this. Okay, component of x square plus component of y square plus component of z square and the whole under root to give the magnitude of a vector. Now magnitude is given by g vector magnitude, that we can write it as like that. Okay, as well, that is equals to under root of gx square plus gy square plus gz square. This is gx component, which is this. Okay, x component, this is gy and this is gz. Let's put the value right here and see what we are gonna get. So g equals, or you can write it like that, that is equals to, what is gx is 2 pi h by a whole square plus gy, which is 2 pi k by a whole square plus gz, which is 2 pi L by a whole square. All right, now let's simplify them. 2 pi square is 4 pi square h square by a square plus 4 pi square k square by a square, 4 pi square L square by a square. Now we can separate a square, we can take the LCM. Okay, a square is the LCM, so we get 4 pi square h square plus 4 pi square k square plus 4 pi square L square. It's like a song. Then we can also take 4 pi square as common, and we can also write 4 pi as 2 pi whole square because I want to write it outside of this outside of the square root. So we can take 2 pi square common out of them and a square like that, and we can write here h square plus k square plus L square, depending upon the kind of form that we want to achieve. You can see here that we have h square plus k square plus L square as separated values. So that is why I took 4 pi square common, which is actually 2 pi whole square as well. Now we can separate the under root on all of these values. So we can write under root 2 pi square oh sorry, under root 2 pi whole square, 2 pi whole square, okay, under root a square, then under root of h square plus k square plus l square. This square and under root cancels out, and this square and under root cancels out as well, and we get 2 pi by a, since the squares and under root cancelled out, and under root of h square plus k square plus l square. That is the magnitude of g vector. Equation number 4, and let's put this value right back into the equation number 2 in order to get this thing. Okay, so we have putting value in equation number 2 in order to get the interplanar spacing. So it's dhkl, that is equals to 2 pi by g magnitude. Okay, so 2 pi by, let's put the value, it's in denominator, so 2 pi by a into h square plus k square plus l square under root. Now this 2 pi cancels out, it's 1 over a, it just jumped in the numerator, so it's a over h square plus k square plus l square under root, and this is d only. Alright, and if you're confused like how these things works, you can even put the value like that, 2 pi divided by 2 pi by a h square plus k square plus l square whole this under root. Okay, when divide sign changes into multiply, what happens is that we have the reciprocal, the denominator becomes numerator and numerator becomes denominator, so a will be written above and we'll have this thing in the denominator. It ensures that you doesn't have any confusions and any mistakes, so it's a over this thing left at the end. Now what we needed is d square, not d only, so we'll take square on both sides, squaring both sides. So after squaring both sides, what we get is d square, that is equals to, you can write hkl in subscript, that's okay, a square under root h square plus k square plus l square whole square. So the square and under root cancels out, and we are left with a square divided by h square plus k square plus l square, and that is what we needed to prove, and hence proved. Alright, so you can see that we have done all of these proofs and it was super easy. Well, that is it for this video. I hope you like it, and if you do, then please like, share and subscribe and keep watching. I upload a lot of helpful stuff in this channel, and yeah, goodbye.